Earth has never completed an orbit. Not one. Not in 4.5 billion years. The path is real. The motion is real. But a completed orbit, a closed loop, a shape that returns to its starting point, has never existed for this planet, and most people go an entire life without knowing that the diagram they were shown in school was wrong in a way that matters. Scientists confirmed the full geometry of this in 1986, when data from hundreds of rotating galaxies finally resolved what the Sun's galactic velocity actually means for the shape of Earth's path through space. Most people never heard about it. The true path is a corkscrew, a helix winding across the galaxy, never closing, never returning. Each lap around the Sun carries Earth 500 billion miles further along the galactic arc. 500 billion miles from the last lap's position, and the total speed carrying you through the universe tonight, measured from the only fixed reference frame the universe actually offers, is 1.3 million miles per hour. Tonight, we trace that path from the corkscrew at our scale outward through the galactic orbit, through the structure that's pulling our entire galaxy off course at 2 million miles per hour, through to the 520 million light-year superstructure we call home, whose name most people have never heard spoken aloud. We'll find the thing scientists named the Great Attractor 4 decades ago, that they've measured carefully since, and that they still cannot see. And by the end of tonight, you'll understand why every astronomer who has truly absorbed all of this has described the same thing afterward. A brief, complete collapse of the feeling that any ground has ever been solid. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Here is the thing nobody draws correctly. The image you carry. Earth making a clean ellipse around the Sun year after year, returning to the same point, a neat, closed loop against a fixed backdrop, is wrong. Not slightly wrong. Not an acceptable simplification. Geometrically, physically, provably wrong. And understanding exactly how it is wrong changes the way every single moment you have ever lived looks from the outside. Earth does orbit the Sunday, that part holds. But while it orbits, the Sun is also moving, carrying everything with it. All 8 planets, all their moons, the asteroid belt, the comets, the clouds of dust, the light, all of it swept forward in a great arc around the center of the Milky Way. The Sun travels this arc at roughly 514,000 miles per hour. So Earth is not making a closed loop in space. It is making a spiral. A helix, a corkscrew stretching across a dimension the usual diagram simply leaves out. Imagine running in a circle on the deck of a ship. From the ship, you trace a circle. From the shore, from a point that isn't moving with you, your path is a long, looping curve that follows the ship across the water. Earth is doing this. It runs its ellipse around the Sun, and the Sun carries it forward, and forward, and forward. The full shape of the path is something between a spring and a wave, winding through the galaxy in a direction no flat diagram has ever shown. This means something specific. Earth has never visited the same point in space twice. Not once. When the dinosaurs moved across this planet, they were in a region of the galaxy we have not returned to. When the first bacteria divided in warm, shallow water, that moment happened at a coordinate no living thing has experienced since. The entire history of this planet is a single forward trajectory through space, never repeating, never closing. It goes further. The helix isn't flat either. The Sun's orbit around the galaxy is not a perfect disk. The Milky Way has a slight warp at its outer edges, and the Sun bobs slowly above and below the galactic midplane as it orbits, rising and falling through the galaxy's densest regions, crossing the central plane roughly every 32 million years. So the corkscrew Earth traces is itself tilting and oscillating, threading through regions of the galaxy that change on timescales. The word year can barely hold. You were not taught this shape, almost no one is. But this is the shape your life is happening in. A long, winding forward line through space that has never once closed and never will. But here's what that shape costs in scale, because putting numbers to the corkscrew changes the word orbit into something that feels like an embarrassing understatement. One orbit of the Sun around the Milky Way takes roughly 225 million years. Scientists call this a galactic year, or a cosmic year. It is not a metaphor. It is a measured duration, calibrated from the Sun's observed velocity and the shape of its arc, confirmed across multiple independent methods. 225 million years. The last time the Sun occupied approximately this position in its galactic orbit, there were no birds, no mammals, no flowers, no grass. The Triassic period had just ended. Dinosaurs had barely appeared. The very first of them, small and bipedal, probably wouldn't be recognizable to a child expecting a Tyrannosaurus. The continents were still arranged as Pangaea. The Atlantic Ocean had not yet opened. That position in space was experiencing the largest mass extinction the planet had yet known, and that was the most recent lap. The Sun has completed this orbit roughly 20 times in its entire lifetime. 20 galactic years. By comparison, your heart will beat approximately 2.5 billion times in a human lifetime of 80 years. The Sun's galactic heartbeat, in those terms, has beaten 20 times. The implication is worth sitting with. Almost everything we call deep history happened within a single galactic year. The rise and fall of the dinosaurs, the entire Cenozoic era of mammals, the emergence of hominids, the development of language, agriculture, cities, every civilization that ever left a record, all of it fits inside the most recent fraction of one lap. Less than a quarter of the current galactic year has elapsed since complex multicellular life first appeared. We are, in the galactic calendar, very early in the current cycle. There is a useful compression. If the entire history of the Earth were a single day, 24 hours, midnight to midnight, then the first single-celled life would appear around 4 in the morning. Complex multicellular life wouldn't arrive until around 9 at night. Dinosaurs would walk the Earth for only about 45 minutes before the asteroid struck at 11:39 p.m. Humans would appear in the final minute, with all of recorded history occupying less than the last second before midnight. A galactic year is that whole day, and the Sun is only 20 days old. In that counting, we have almost no galactic memory. We are newcomers to our own orbit, and the galaxy has already changed enormously in the time since the Sun first appeared in it. What it changed into, and what the Sun has passed through in those 20 laps, is where the path becomes something more than a beautiful abstraction. The Milky Way is not a uniform disk. Its mass concentrates toward the galactic midplane, the central equator of the galaxy, where molecular clouds are densest, star formation most active, and gravitational turbulence most pronounced. This plane is where the galaxy is most alive, in the energetic sense. And the Sun crosses it twice every galactic year. At the current rate of vertical oscillation, the Sun passes through the galactic midplane roughly every 32 million years. Once heading above, once returning below, each crossing takes it through the most radiation-rich, most dust-dense region the solar system encounters on any regular schedule. In 1984, paleontologists David Raup and J.J. Sepkoski published a paper identifying an apparent cycle in the mass extinction record of marine animals, a periodic spike in extinction rate occurring approximately every 26 to 30 million years, going back at least 250 million years. The number matched, within the uncertainty of both measurements, the period of the Sun's oscillation through the galactic plane. The paper was controversial when it appeared. It remains partly contested, but the correlation did not disappear under additional scrutiny. It held, and in some analyses strengthened, as more data came in. The mechanism is still debated. Some researchers propose that mid-plane crossings disturb the Oort cloud. the distant reservoir of comets that surrounds the outer solar system, dislodging periodic showers that rain inward toward the planets. Others pointed to cosmic ray flux increases as the solar system enters denser gas clouds, possibly affecting cloud formation and climate stability. No single mechanism has been confirmed. The cause may be several factors working in combination, or none of the proposed ones, or something not yet identified. But the observation stands. The solar system is not orbiting in neutral space. It bobs through regions of varying density and gravitational energy, and those crossings may have written themselves into the fossil record more than once. The Earth's biological history, the extinction pulses that cleared the way for mammals, for every living thing that came after, may have been timed, in part, by the geometry of an orbit too large for any living thing to perceive from inside it. The next crossing of the galactic midplane is estimated to be roughly 10 to 15 million years from now. We did not choose when to cross. We simply arrive. The spiral arms of the Milky Way look, in images, like solid structures, bright, curved lanes sweeping outward from the galactic center. They appear to be the skeleton of the galaxy, permanent architecture, the defining feature of the whole system. This reading is mostly incorrect. The spiral arms are not physical structures that stars belong to permanently. They are density waves, regions of slightly higher compression moving through the disk of the galaxy, somewhat like a pressure wave moving through water. When gas and dust enter the compressed region, star formation accelerates. New, hot, bright stars form, burn fast, and explode, generating the light that makes the arm visible. But the stars themselves are not locked to the arm. They pass through it, spending time in the denser region before emerging on the other side. The Sun has passed through spiral arm regions before. It will do so again. The current position of the solar system places it in or just inside the Orion arm. A smaller, partial arm structure, but the Sun's orbital speed and the density wave's rotation rate are different, meaning the Sun slowly drifts in and out of these regions as the rates diverge over millions of years. Inside a spiral arm, star formation is more active, which means more massive stars, more supernovae, more ultraviolet radiation, and cosmic ray flux than in the quieter inter-arm regions. Some researchers have proposed that Earth's climate history shows signals of arm crossings in the form of elevated glaciation periods, that moving through denser interstellar gas and radiation over hundreds of millions of years contributed to the sequence of ice ages embedded in Earth's geological record. The evidence is fragmentary. The signal is difficult to isolate from other processes. But the framework is coherent. The medium changes as we move through it. The medium has always changed. The solar system is not orbiting in vacuum, in the stable, featureless sense. It is moving through a galaxy that is alive, structured, dynamic, full of regions where the conditions for chemistry, for biology, for the persistence of anything on the surface of a planet shift in ways that leave marks. But the spiral arms are small perturbations compared to what lies outside the galaxy entirely. The Milky Way belongs to a gravitational family called the Local Group, roughly 50 galaxies, most of them dwarf systems, a few of them large, bound together by mutual gravity in a volume roughly 10 million light-years across. Within it, two major galaxies dominate: the Milky Way and Andromeda. The rest are satellites and borderline cases, orbiting one or the other, or drifting in the gravitational uncertainty between them. This group, as a collective, is not stationary. It is falling slowly, continuously, in a direction and at a velocity that took decades to measure with any precision. The fall was first clearly identified through an anomaly. When astronomers mapped the velocities of galaxies in our cosmic neighborhood, measuring how fast they were receding due to the expansion of the universe, they found that some galaxies weren't receding at exactly the rate the expansion would predict. They had an additional component of velocity, a peculiar velocity, not expansion, but actual motion through space, above and beyond the general cosmic flow. This peculiar velocity pointed in a consistent direction. Something was pulling the local group in addition to the expansion. The pull was real and measurable. It implied something massive, somewhere beyond our direct line of sight, exerting gravitational influence across hundreds of millions of light years. Scientists named the source before they could see it, the Great Attractor. The name is accurate rather than dramatic. The Great Attractor is not a single object. It is a concentration of mass, galaxies, galaxy clusters, dark matter, centered roughly 250 million light-years away in the direction of the constellations Centaurus and Hydra. Its mass is estimated at something close to 10,000 times the mass of the Milky Way, though pinning that number down precisely remains an ongoing problem. We are moving toward it at roughly 2 million miles per hour, not in a straight line. The expansion of the universe curves and complicates the trajectory, but the pull exists. It is measurable. And it has been consistent for as long as the solar system has been old enough to have an orbit. We will never reach it. The expansion of the universe is accelerating, meaning the fabric of space is stretching faster than gravity can pull us toward distant mass. But we are still moving toward it. The vector is real. The motion continues tonight, quietly, without our needing to do anything. And if the Great Attractor is pulling us, then the question that follows becomes unavoidable. What is pulling it? 2.5 million light-years away, Andromeda is approaching at approximately 250,000 miles per hour. This has been known for decades, but the standard framing, Andromeda is approaching, places the agency outside the Milky Way as if we were stationary and something were coming. This framing is not accurate. Both galaxies are in motion. Both are curving toward a gravitational center of mass that neither fully occupies. The merger, which will not be a collision in any meaningful sense, since galaxies are mostly empty space, is estimated to begin in roughly 4 billion years, with the two systems intertwining, briefly separating, and then merging over the following 2 to 3 billion years into a single elliptical galaxy. During this process, the stars of both galaxies will be redistributed. Individual stars are unlikely to collide. The distances between them are far too large. But the gravitational dynamics will scramble orbital paths, flinging some stars into wide new orbits, pulling others toward the center of the merged system. The Sun, currently at 26,000 light-years from the galactic core, may be displaced into a completely different region of the combined galaxy. What goes unsaid in most descriptions? This process has already begun, in the gravitational sense. The two galaxies are embedded in each other's dark matter halos, the vast invisible spheres of mass extending far beyond the visible disk of each system. In this technical sense, the Milky Way and Andromeda are already overlapping. The merger has, in the deepest gravitational layer, already started. This is not alarming on the timescale of a human life, or a civilization, or a species. 4 billion years has no emotional grip, but it has physical reality. The Milky Way is not a permanent structure. It is a temporary arrangement of matter, moving toward a transformation that gravity has already decided, and the motion carrying us toward Andromeda is happening right now, continuously, without pause. The orbit, the Great Attractor, the approach of Andromeda, these are all simultaneously true, all happening at once, all contributing to the single measurable number that describes where you actually are in motion tonight. There is a way to measure how fast you are actually moving, not relative to Earth, not relative to the Sun, not relative to the galactic center, but relative to the universe itself, or rather, relative to the oldest light in the universe, which functions as the closest thing to a fixed reference frame that physics has ever found. In 1964, two radio astronomers at Bell Labs, named Arno Penzias and Robert Wilson, were attempting to eliminate a persistent hiss in their antenna. They pointed it at everything they could think of: the hiss remained. It came equally from all directions, at all times, regardless of where they aimed. It turned out to be the cosmic microwave background, the ancient thermal glow left over from 380,000 years after the Big Bang, now cooled to just 2.7 degrees above absolute zero, filling the entire observable universe in every direction, uniformly almost. There is a tiny asymmetry. One side of the sky appears very slightly warmer than the other. The temperature difference is about 1 part in 1,000, small enough that early measurements missed it entirely. But it is not noise. It is the signature of motion. The solar system, and by extension the Milky Way, and by extension the entire local group, is moving through the CMB rest frame at a measurable velocity. That velocity is 1.3 million miles per hour, toward a region of sky near the constellation Leo. This number combines all the layers: Earth's orbit, the Sun's galactic arc, the Milky Way's infall toward the Great Attractor, into a single vector relative to the background light of the universe. 1.3 million miles per hour, 600 kilometers every second. You feel none of it. The sensations available to human bodies, wind, G-force, pressure, are all designed to register changes in relative motion, not absolute velocity. The air around you is traveling at the same speed. The chair or bed or floor beneath you is traveling at the same speed. There is nothing to push against, no differential the body can register. This is not a failure of perception. It is a feature of physics. Motion becomes felt only when it is uneven. When something accelerates, or decelerates, or encounters resistance from something moving differently, you are moving at 600 kilometers per second. And the universe provides no indication of this whatsoever, because everything you have ever touched is moving with you. The only instrument sensitive enough to detect it is the sky itself. And the sky tells you precisely where you are going. In the 1,970 seconds and early 1,980 seconds, a group of 7 astronomers, informally called the 7 Samurai, spent years mapping the velocities of elliptical galaxies scattered across the local universe. They were looking for departures from the expected Hubble flow. What they found, published in 1988, was a coherent streaming motion involving galaxies spread across more than 100 million light-years, all flowing in the same direction, all heading toward the same approximate region of sky. The structure producing this flow was not visible. It lay behind the zone of avoidance, a broad strip of sky roughly 20 degrees wide, obscured by the disk of our own galaxy. The dust and gas of the Milky Way is thick enough in this band to block most optical and near-infrared light from sources beyond, making the region effectively opaque to standard observation. Whatever sits at the heart of the Great Attractor's flow, we cannot see it directly. We can only see its effects on the galaxies around it. Radio telescopes, which penetrate galactic dust, have gradually mapped parts of this obscured region. What they found is a massive cluster of galaxy clusters, the Norma cluster and surrounding overdensities, consistent with the observed infall pattern. But the total mass required to explain the streaming motion exceeds what the visible structures can account for. Something else is there, presumably dark matter, in quantities we can only estimate from the flow it produces. This is a slightly unsettling arrangement, the dominant gravitational influence on the Milky Way's trajectory. On the path your body is tracing through space tonight is something we cannot observe, in a region we cannot see, producing effects we measure only indirectly through the velocities of other galaxies. We know approximately where we're going. We don't fully know what's there. And the Great Attractor may not be the final destination in any case. Surveys in the early 21st century revealed that the Great Attractor is not the sole driver of the local infall pattern. Something even more massive lies farther away, in the same general direction. The Shapley concentration, a supercluster of galaxy clusters 200 million light-years beyond the Great Attractor, containing something like 10,000 galaxies in a region that, by cosmic standards, is almost claustrophobically dense. We are falling toward the Great Attractor. The Great Attractor may itself be falling toward Shapley. The chain of gravitational dominoes extends further than our current instruments can fully resolve. This is where we still don't know. Not an admission of defeat, an accurate statement of the edge of current knowledge. The chain continues. We are following it in real time, without knowing where it ends. In 2014, a team of cosmographers led by Brent Tully at the University of Hawaii published a paper in Nature that redefined our cosmic address. Using data from hundreds of thousands of galaxy-peculiar velocities, those departures from the Hubble flow that revealed gravitational attraction, they mapped the full flow pattern of the local universe and identified the boundaries of the structure that contains us. They called it Laniakea. The name comes from Hawaiian, Lani for heaven, Akea for spacious or immeasurable. The structure is 520 million light-years across. It contains roughly 100,000 galaxies, including the Milky Way, Andromeda, the Local Group, the Virgo Cluster, and the Great Attractor region. The total mass is estimated at something close to 100 quadrillion solar masses, 100 million billion times the mass of the Sunday. This is not a wall or a box. Tully and his colleagues defined Laniakea not by physical boundaries but by a basin of attraction. All the galaxies within it are flowing, in principle, toward a common gravitational center. They belong to the same infall pattern. The Milky Way is in this basin. There is something important to understand about Laniakea. It is almost certainly not gravitationally bound as a whole. The expansion of the universe is pulling its outermost regions apart faster than the internal gravity can hold them together. Laniakea will not remain a coherent structure indefinitely. Over tens of billions of years, the accelerating expansion will scatter its member galaxies beyond each other's gravitational reach, and the structure we currently call home will dissolve. Not catastrophically, but gradually. The way a pattern in water disperses when the force that created it is spent, but it exists now, and for the past several billion years, the Milky Way has been a member of this enormous, slowly flowing, loosely bound family of galaxies. Our current position within Laniakea places the Milky Way near the periphery, near the edge of the basin, where the infall toward the central attractor competes with the expansion driving things apart. Our cosmic address. In full, Laniakea supercluster, Local Group, Milky Way galaxy, Orion Arm, Solar System, Earth. Each layer is in motion. Each is falling towards something larger, and the largest motion of all, the CMB vector, is the one that tells us something has been pulling everything for billions of years. We still don't know what occupies the deepest center of the Laniakea basin. The flow is real. What drives it is still being mapped. In the 1,960 seconds and 1,970 seconds, an astronomer named Vera Rubin was measuring something considered relatively routine, the rotation curves of spiral galaxies. The idea was straightforward. Measure how fast stars at different distances from a galaxy's center are orbiting, and you could work out the mass distribution of the galaxy. Rotational physics predicted a clear pattern. Stars at the outer edges should orbit more slowly than stars near the center, just as the outer planets orbit more slowly than the inner ones. It's the same pattern a spinning fan makes. Fast at the hub, slower at the blade tips. Galaxy after galaxy, the pattern was absent. The outer stars were orbiting at roughly the same speed as the inner stars, or in some cases faster. The rotation curves were flat, or slightly rising, where they should have been declining. Something was providing the gravitational grip that the visible matter all the stars, all the gas, all the dust could not account for. What Rubin had found was evidence for dark matter. More precisely, the evidence suggested that galaxies were embedded in enormous extended halos of matter that didn't emit any light but did exert gravity, halos far larger than the visible disk, extending in some cases to 10 or more times the radius of the visible stars. Without these halos, the rotation curves couldn't be explained. With them, the numbers fell into place. Rubin wasn't the first to propose dark matter existed. Fritz Zwicky had suggested it in the 1,930 seconds based on galaxy cluster dynamics. But her work, systematically applied to galaxy after galaxy across decades, made the case nearly impossible to ignore. The evidence was not theoretical. It was observational. Curve after curve, galaxy after galaxy, the same departure from expectation. By the 1,980 seconds, dark matter had moved from fringe hypothesis to mainstream physics. What this means for Earth's motion is direct. The dark matter halo of the Milky Way is the primary container of the galaxy's mass. The orbit of the Sunday, the galactic year, the corkscrew, everything takes place within a gravitational well that is mostly invisible, extended far beyond anything visible in any photograph of the Milky Way. The galaxy we inhabit is smaller than the structure we orbit inside. The visible disk is, in some sense, the lit interior of a much larger dark container. Rubin never received the Nobel Prize she arguably deserved. She died in 2016, her work foundational to everything that followed, including the satellite missions that mapped the CMB dipole, the signature of the very motion toward the Great Attractor, for which other researchers received recognition. The irony is not small, and it sits in the record. Without dark matter, the Milky Way as we know it would not hold together. The stars in the outer disk, including the Sunday, would be moving too fast for the gravitational pull of the visible matter to retain them. They would drift outward and escape the galaxy over time. The fact that they don't, that the disk maintains its shape and the rotation curve remains flat, is evidence that additional mass is present throughout. The Sun orbits the galactic center at roughly 26,000 light-years, completing one orbit in approximately 225 million years. The speed required for a stable orbit at that distance, given only visible matter, should be significantly lower than what we observe. The observed orbital speed implies a total enclosed mass roughly 10 times larger than the visible mass within that orbit. The difference is dark matter. This is not a small correction. The Milky Way's dark matter halo is estimated to contain anywhere from 6 to 40 times as much mass as all the stars, gas, and dust in the visible galaxy combined. It extends to at least 3 times the radius of the stellar disk, possibly much more. The outer boundary of the dark matter halo is genuinely unknown, because the objects needed to probe it become sparse at those distances, and the measurements grow increasingly uncertain. What is known is this. The dark matter halo is what makes the orbital motion of every star in the galaxy consistent with the observed rotation curve. It provides the gravitational scaffolding that keeps the disk intact, that channels the infall of gas from the surrounding medium, that determines how the galaxy evolves and merges with other systems over time. Dark matter is not an exotic footnote to the story of Earth's motion. It is the primary driver. The corkscrew path Earth traces through space, the galactic year, the stable orbit that has kept the solar system in a relatively quiet region of the galaxy for billions of years. All of this runs on dark matter gravity. The force that makes the entire journey possible is one we cannot see, cannot touch, cannot measure directly, and have not yet fully characterized. Earth moves through space on the back of something we don't understand. And we don't understand it. Zoom out far enough from Laniakea and the individual structures, galaxy clusters, superclusters, filaments, walls. resolve into a pattern cosmologists call the cosmic web. It is the largest known structure in the universe. A three-dimensional network of filaments, sheets, and nodes, with vast empty voids between them, spanning scales that make individual galaxies look like dust motes clinging to a thread. The filaments of the cosmic web are not arbitrary. They formed because of tiny quantum fluctuations in the earliest moments of the universe, microscopic unevennesses in the density of the primordial plasma, imprinted on the fabric of space in the first fraction of a second of existence. Gravity amplified these fluctuations over billions of years, drawing matter toward the denser regions, building the first structures, the first galaxies, the first clusters, until the web we observe today emerged as a fossil record of those original differences. The Milky Way is a node in this web, connected to the filaments that feed into Laniakea, embedded in the foam of a universe that is structured at every scale. And the motion of the Milky Way, its infall toward the Great Attractor, its membership in Laniakea, follows the gravitational gradient of this web. We are not moving randomly. We are moving along a path that the web imposed on our region of space, a path that has been curving in the same general direction for billions of years. The cosmic web is not static. The voids are expanding, not because matter is leaving them, but because the accelerating expansion is inflating the empty regions faster than gravity can refill them. The filaments are thinning as matter drains toward the nodes. Galaxy clusters are becoming more isolated. Over tens of billions of years, the web will thin and fragment, leaving island universes in a void so deep that they could not detect each other even with the most sensitive instruments imaginable. But in this moment, the web still connects, and we are moving through it in the direction the web's gravity has directed us for as long as anything in this galaxy has been old enough to follow a path. The sun is not simply sitting in the interstellar medium, it pushes against it. Continuously, in every direction, at all times, the sun emits a stream of charged particles, electrons, protons, and heavier ions. Moving outward at roughly 1,000,000 miles per hour in the slower regions of the wind, twice that in the faster. This is the solar wind, and it creates a structure that extends from the sun to a distance far beyond the orbit of Pluto, defining the practical boundary between what belongs to the solar system and what belongs to the galaxy. This structure is called the heliosphere. It is not a perfect sphere. The solar system's motion through the interstellar medium compresses it on the side facing the direction of travel, creating a blunted leading face, and stretches it into a long tail on the trailing side, like a comet shape pulled by its own momentum. The leading edge, where the solar wind first encounters the interstellar medium and slows abruptly, is called the termination shock. Beyond that is the heliosheath, a turbulent transition region where the solar wind decelerates dramatically. And at the outer boundary, where the solar wind finally gives way to the interstellar medium, is the heliopause. The Voyager probes gave us the first direct measurements of where this boundary falls. Voyager 1 crossed the heliopause in August 2012, at a distance of about 11 billion miles from the Sunday. Voyager 2 crossed it in November 2018, at a slightly different distance on a different trajectory, revealing that the heliosphere is asymmetric, more complicated in shape than models had predicted. Everything within the heliopause is, in some sense, inside the Sun's atmosphere. The planets, the asteroid belt, every comet that falls through the inner system, every probe humanity has ever launched. All of it exists inside this bubble. Outside, the interstellar medium begins. A different plasma, different magnetic field orientation, different particle energies. The heliosphere moves through the interstellar medium as the solar system orbits the galaxy. As we move, the bubble plows through whatever gas and dust lies in its path. Right now, the heliosphere is crossing the edge of what's called the local interstellar cloud, a warm, relatively dense region of partially ionized hydrogen and helium that the solar system entered somewhere between 44,000 and 150,000 years ago. The solar system may exit this cloud within a few thousand to tens of thousands of years. When we exit, the external medium will change. How the heliosphere responds, whether it expands or contracts, how the cosmic ray shielding shifts, is an active area of research. The boundary we live inside is not permanent. It has changed before, and it will change again as the path carries us through regions of the galaxy that differ from the one we occupy now. The solar system is not in a typical neighborhood, the region of the galaxy around us. Extending to roughly 1,000 light-years in most directions, is unusually empty. The interstellar medium in the immediate vicinity of the Sun is far less dense than the galactic average, hot, thin, and ionized. This unusual condition has a name: the local bubble. The local bubble was probably formed by a series of supernovae occurring over the past 10 to 20 million years. As massive stars exploded, their shockwaves drove surrounding gas outward, clearing a roughly spherical region and heating the remaining gas to temperatures of millions of degrees. The cavity carved out by those deaths is what the solar system currently inhabits. This has a direct implication for the heliosphere. Because the local interstellar medium is so thin and hot, the solar wind can push further against it. The heliosphere is larger than it would be in a denser medium. In a denser region of the galaxy, the heliopause might be significantly closer, the cosmic ray shielding weaker, the interstellar environment more intrusive on the inner planets. There is a chain of causality worth holding. Massive stars formed from the galaxy's gas, lived fast, and exploded, carving out the cavity the Sun now moves through. And the solar system itself was formed partly from the debris of still earlier supernovae. The iron in Earth's core, the calcium in human bones, the oxygen in every breath, came from stars that died before the Sun was born. Those same types of explosions continued in the local neighborhood over the past few tens of millions of years, built the unusually quiet, clear region that the heliosphere expands into now. The stars that made us also made our neighborhood. They carved the room in the galaxy that we currently occupy. The violence that built the elements in every living thing is the same violence that cleared the space we drift through. A note of something any analogy misses. The local bubble is not a perfect void. It contains the local interstellar cloud, a smaller, denser region the solar system is currently passing through, and probably several other cloudlets scattered through it. It is a cleared region rather than true emptiness, but relative to the galactic average, it remains an unusually thin and hot volume of space. We are inside a bubble blown by dead stars, moving through the galaxy in the direction those deaths cleared. The heliosphere does not block everything. It reduces the flux of galactic cosmic rays, high-energy particles, mostly protons and heavier atomic nuclei, accelerated to nearly the speed of light by supernovae, pulsars, and other energetic events distributed across the galaxy. But it does not stop them. A significant fraction penetrate all the way to the inner solar system, where they interact with the Earth's magnetic field and atmosphere, and in some cases reach the surface. Cosmic rays are not acutely dangerous to human health under ordinary circumstances. The atmosphere provides substantial shielding, and the Earth's magnetic field deflects charged particles toward the poles, which is the mechanism behind the aurora. At sea level, cosmic ray exposure contributes only a small fraction of the background radiation a person receives annually. At altitude, the exposure increases. In aircraft at cruising altitude, cosmic ray dose rates are measurably higher than at the surface. In low Earth orbit, higher still. Astronauts on long-duration missions outside the magnetic field or on trajectories toward Mars receive radiation doses that represent a genuine health concern, one of the harder engineering problems in deep space travel. The heliosphere is their partial shield. Without it, the flux would be substantially greater. As the solar system moves through different regions of the galaxy, the cosmic ray flux changes. In denser interstellar regions, the heliosphere compresses, providing less shielding. Near active star-forming regions or recent supernova remnants, cosmic ray energies and flux can be elevated significantly. The exposure history of the inner solar system to cosmic radiation has varied over galactic history, in ways still being worked out from isotope records in deep-sea sediments and Antarctic ice. You are, right now, being struck by particles launched from the depths of distant stars. The rate is low. The effect on your body is negligible, but it is happening continuously, and it is the galaxy touching you directly, across distances that no other physical process can span in the same moment. When the Voyager probes crossed the heliopause, when their instruments registered that the outward-flowing solar wind had given way to the inward-flowing interstellar medium, scientists did not find a sharp boundary. They found a region. The heliopause is a transition, not an edge. Solar and interstellar plasmas intermingle in the heliosheath. The magnetic field orientation shifts, but not abruptly. The particle energies change across a gradient. If you are traveling outward through the heliosphere in a spacecraft without instruments, you would not notice crossing it. There is no wall, no surface, no moment of crossing. The sun's territory thins, gradually, into something else. Something similar is true of every boundary in the universe at sufficient resolution. Galaxy halos blur into the intergalactic medium. Cluster edges blur into the cosmic web filaments. The local bubble has no sharp wall. It grades into the surrounding interstellar clouds. The Laniakea supercluster has a defined basin of attraction but no physical edge, just a place where the gravitational flow changes direction. The universe draws its lines in gradients, not walls. The structures we name, the heliosphere, the galaxy, the supercluster, are real in the sense that they describe coherent patterns, regions where something important is organized differently. But their edges are almost never what the name implies. They breathe, they blend, they blur into each other at their margins, the way a held breath eventually becomes the room's air. The sense of enclosure, of being inside the solar system, inside the galaxy, inside Laniakea, is accurate enough for most purposes. But pressed carefully, each boundary softens. What remains after the softening is not chaos. It is something more like continuity. The universe as a single object that happens, in some places, to be organized more densely than in others. The outermost edge of what we carry with us as we move through space, the truly outermost, is something far beyond even the heliopause. And its name is worth saying slowly. The Oort cloud has never been directly observed. Not one of its objects has been imaged. Its existence is inferred entirely from the behavior of comets that occasionally fall through the inner solar system. Comets with very long orbital periods, arriving from random directions in the sky, moving on orbits barely bound to the sun at all. The mathematics of those orbits points backward to a distant shell of small bodies loosely attached to the solar system, floating in the space between the sun and the nearest stars. The Oort cloud is estimated to begin at roughly 2,000 times Earth's distance from the sun, and to extend to perhaps 100,000 times that distance, roughly a quarter to halfway to the nearest star. At its outer edge, the sun's gravitational pull on any individual object is so weak that a passing star or the differential gravitational pull of the galactic disk, called the galactic tide, is enough to disturb the orbit. This is, in fact, the proposed mechanism by which comets from the Oort cloud are occasionally sent inward. Gravitational perturbation from passing stars, or the galaxy itself nudges objects out of their stable orbits and sends them on long, arcing infall trajectories toward the Sunday. The Oort cloud moves with us through the galaxy. It is as much a part of the solar system as the planets, even though it is so diffuse and distant that it is practically indistinguishable from the surrounding interstellar space. It represents the outer membrane of the solar system's gravitational domain, the edge of everything that is still more attached to the Sun than to anything else. How many objects are in the Oort cloud? Estimates range from hundreds of billions to several trillion. At the outer edge, these objects are spaced enormous distances apart, not a dense shell, but a sparse, globe-shaped swarm of ice and rock, drifting in near total darkness at temperatures just a few degrees above absolute zero, held in orbit so slow and so wide that a single lap takes millions of years. These objects are original material from the formation of the solar system, unchanged for 4.5 billion years, preserved in cold so deep that chemistry nearly stops. When one falls inward and becomes a comet, it delivers material to the inner solar system that has not been significantly altered since before the Earth existed. The Oort cloud is, in this sense, a time capsule. We pass through the galaxy carrying a vast outer shell of primordial material, and from time to time, the galaxy reaches in and flicks a piece of it toward us. Here is a number that the usual unit fails to hold. A human life of 80 years, lived without leaving Earth. During that life, Earth completes 80 orbits around the Sun, each covering roughly 580 million miles. That alone is 46 billion miles of orbital path. But the Sun, carrying Earth, also travels at 514,000 miles per hour along its galactic arc. Over 80 years, the Sun moves approximately 360 billion miles along its galactic orbit. Add those together, and a human lifetime of apparent stillness, of never leaving the planet, of sleeping in the same bed for decades, covers something in the range of 400 billion miles through the galaxy. Against the CMB rest frame, the combined velocity adds even more distance. 80 years, 1.3 million miles per hour, amounts to roughly 900 billion miles of total motion through the structure of the universe. 900 billion miles, the distance from the Sun to the nearest star, is about 25 trillion miles. A full human lifetime of stillness traces a path through space equivalent to roughly 3.5% of the journey from the Sun to the nearest stellar neighbor. This is not a comparison designed to make the number feel smaller. It is a comparison that makes the number feel like what it is: enormous, personal, and entirely invisible. The motion has been accumulating every moment since the first breath. Every second of sleep, every hour of sitting still, every year that passed without moving more than a few miles from home. None of it was felt, none of it appears in any record. But it happened, every moment, at speeds the body was never built to register, and no one who came before you, no ancestor, going back to the first cell that divided in warm water, ever passed through the same point in space that you are passing through right now. The universe has never recycled a position. It has only moved forward. And every life that has ever happened on this planet has happened in a location that was first time ever and will not recur. There is a way of saying this that feels like comfort, and a way that produces a sensation more like the ground shifting. The comfortable version: every moment is new. Every second of the journey is unprecedented. There is no template for right now, because right now has never happened. The other version: there is no returning, not to this location in space, not to this configuration of matter, not to this specific arrangement of conditions. Everything that exists is passing through its position for the first and only time. There is no recovery from the motion. There is no going back, even in principle, because the coordinate that was back has moved on. Physicists are careful about the word return. Some formulations of thermodynamics suggest that, in principle, given infinite time, the exact configuration of any system could recur, the Poincaré recurrence theorem, but the timescales are so vast as to be meaningless to anything that experiences time. Longer than the current age of the universe raised to powers that cannot be written in ordinary notation. And in an expanding, accelerating universe, the recurrence timescales grow without bound as the universe cools. there will not be a return. This planet, this orbit, this configuration, it exists once. The moments of quiet that happen on it exist once. The sleeping and the breathing and the slow turning of seasons happen in locations that have never been visited before and will not be visited again by this arrangement of matter in this state of the galaxy's position. It is possible to sit with this as a fact, not to resolve it into comfort or into unease, just to hold it, the way you hold the weight of something very old that has its own completeness independent of what you feel about it. The center of the Milky Way is a region of intense activity, a dense cluster of stars, enormous molecular clouds, and at its core, a supermassive black hole with a mass of about 4 million solar masses called Sagittarius A. This is the gravitational anchor of the galaxy. The Sun orbits this center, but not precisely around it. The Sun orbits the center of mass of all the matter within its orbital radius, which includes not just Sagittarius A, but all the billions of stars, the gas and dust, and the dominant contribution of the dark matter halo. The black hole at the center is massive compared to ordinary stars, but a tiny fraction of the galaxy's total mass. It is not the anchor it might appear to be. Moreover, the Sun's orbit is not a perfect ellipse. The galactic mass distribution is not spherically symmetric. The spiral arm density variations, the galactic bar in the central region, the warp in the outer disk, the complex shape of the dark matter halo. All of these introduce perturbations to the orbital path. The orbit is approximately circular at the galactic scale, but in detail, it oscillates slightly inward and outward, a radial breathing on top of the overall circulation, adding yet another layer of motion to the corkscrew. This means the Sun's distance from the galactic center is not fixed at 26,000 light-years. It varies by several hundred to a few thousand light-years over the course of each galactic orbit, as the radial oscillation carries it inward and outward around the mean radius. The true path requires at least 3 dimensions: a variable radial component, a vertical oscillation through the galactic plane, and perturbations from large-scale galactic structure. To draw it accurately would require a map that no one has made, because many of the inputs are still being measured. The true orbit is known broadly. In precise detail, it remains an open problem in galactic astronomy. We know roughly where we are. We do not know our position with the precision we have for a satellite in low Earth orbit. The uncertainty in the Sun's galactic orbital parameters, the exact distance to the center, the precise period, the detailed shape of the path, remains substantial. Between the stars, the interstellar medium is not a single substance with a single set of properties. It is a collection of phases, occupying the same large volume at wildly different temperatures and densities, each defined by the local balance of heating and cooling processes operating in that region. The cold neutral medium, dense clouds where hydrogen exists in atomic form, has temperatures around 100 degrees above absolute zero. The warm neutral medium that fills much of the volume between the dense clouds ranges from 6,000 to 10,000 degrees. The warm ionized medium, heated by ultraviolet radiation from hot stars, occupies similar temperature ranges but differs in composition and behavior. And the hot ionized medium, the plasma that fills the local bubble and other supernova-heated regions, has temperatures of hundreds of thousands to millions of degrees. The solar system passes through these phases as it orbits the galaxy over geological time. Different interstellar phases have different densities, different magnetic field structures, different particle compositions. The heliosphere's response to each is different. It compresses in dense cold gas, expands in thin hot plasma. The cosmic ray flux inside the heliosphere varies with the external medium. The amount of interstellar dust and gas that reaches the inner solar system changes. The Earth, from inside the heliosphere, feels these changes only indirectly and over long timescales. But the changes are real, and the record of past interstellar environments may be preserved. In isotope ratios in deep-sea sediments, in Antarctic ice cores, in concentrations of certain radioactive isotopes, in lunar regolith. waiting to be read by instruments sensitive enough to distinguish one interstellar phase from another in the geological record. The medium we're moving through has a memory. We're still learning how to read it. The nearest star to the Sun is Proxima Centauri, at approximately 4.2 light-years. This is the current closest stellar neighbour, but it has not always been the closest, and will not remain so. Stars move. Relative velocities between stars in the galactic neighbourhood are typically tens of kilometers per second, slow by cosmic standards, but significant on galactic timescales. Over the history of the solar system, many stars have made close passes. Close in interstellar terms means anything within a few light-years, far enough that direct interaction with the planets is impossible, but close enough to gravitationally perturb the Oort cloud, potentially dislodging comets and sending them inward on new trajectories. Estimates suggest the Oort cloud is disturbed by a passing star every few tens of millions of years on average, which is consistent with the apparent comet shower periodicity. In the future, the passes will continue. Astronomers using data from the Gaia Space Telescope, which measures the positions and velocities of over 1 billion stars with unprecedented precision, have calculated the future close approaches of thousands of stars in the solar neighbourhood. The most significant predicted approach involves a star called Gliese 710, a dim orange dwarf currently about 63 light-years away, which will pass through or very near the outer Oort cloud in approximately 1.3 million years at a closest approach of perhaps less than 1 light-year. This will be the most significant stellar intruder in the past 11 million years, and it will likely trigger an enhanced shower of comets into the inner solar system over the hundreds of thousands of years following the encounter, 1.3 million years. An unreachable future by any current measure of human civilization, but registered by the same orbital dynamics that have been operating uninterrupted since the solar system formed. The galaxy is not empty around us. 200 billion stars are all in motion simultaneously, each tracing their own version of the corkscrew, each on a path that occasionally sweeps close enough to matter. For a long time, the Milky Way was assumed to be a relatively flat disk. The spiral arms, the galactic plane, the disk structure all modelled as lying in a common plane, like a thin platter of stars. This model, it turns out, was a simplification that the outer disk does not respect. The outer disk of the Milky Way is warped. This was suspected for decades based on observations of the neutral hydrogen distribution at large galactic radii, which showed a clear-shaped deviation from the disk midplane. But pinning down the nature of the warp with precision required better data. In 2019, a team used a catalogue of classical Cepheid variable stars, pulsing stars whose luminosity follows a strict period luminosity relationship, making them reliable distance indicators. To map the three-dimensional distribution of young stars in the outer Milky Way, what they found confirmed the warp and provided its most precise characterization. The outer disk begins to deviate from the midplane at roughly 40,000 light-years from the center, and by 70,000 light-years, the deviation reaches about 5,000 light-years above or below the average plane, depending on which side. The warp is likely caused by gravitational interaction with the Large and Small Magellanic Clouds, the Milky Way's two largest satellite galaxies, whose orbits have been tugging on the outer disk over billions of years. The warp itself rotates, completing one rotation in roughly 500 to 600 million years. The Sun is in the inner disk, not the warped region, but the warp is a reminder that the galaxy's geometry is more complex than any simple model. The structure the Sun orbits through is not planar. The galaxy is alive, in the mechanical sense, changing its shape on the timescales that define our orbit, responding to the pull of its own satellites, shaped by interactions that have been ongoing for billions of years. We orbit inside something that is itself in motion, itself being pulled, itself deforming slowly in response to forces that operate across a scale that makes the inner disk seem like a stable, quiet place, which, by galactic standards, it is. Sagittarius A, the black hole at the center of the Milky Way, is currently in a relatively quiet state. By galactic standards, quiet is still extraordinary. Observations across the electromagnetic spectrum reveal that Sagittarius A flares regularly, brief brightening events lasting from minutes to hours, occurring several times per day, caused by material near the black hole falling inward or passing close enough to be partially disrupted. During these flares, the emission from the central region increases by factors of tens to hundreds. Something is always falling into the center. The center is always releasing energy in response. More dramatically, scientists have identified structures called the Fermi bubbles, two enormous lobes of gamma-ray emission extending above and below the galactic plane for tens of thousands of light years. Centered on the galactic core, discovered in 2010 using the Fermi Gamma-Ray Space Telescope, they appear to be the remnants of a massive energy release from Sagittarius A, or from intense star formation in the galactic center region that occurred perhaps a few million to tens of millions of years ago. The energy involved in creating these structures is on a scale that requires comparisons that don't work well in ordinary language. Millions of supernovae, compressed in time, is a rough and inadequate approximation. The Fermi bubbles extend perpendicular to the disk, outward through the galactic halo, and are still expanding. They carry material and energy out of the galactic center region, affecting the structure of the halo and the surrounding medium in ways that are still being mapped. The Sun, at 26,000 light-years from the center, is far enough from the galactic core that none of this activity has direct effects on the inner solar system in the current epoch. But the galactic center was more active in the geological past. The Fermi bubble events probably occurred while complex life was already established on Earth. Whether the enhanced radiation had any measurable effect on the biosphere is an open question that the geological record has not yet clearly answered. The Milky Way did not form alone, and it did not grow in isolation. Like virtually all large galaxies in the universe, it grew by consuming smaller galaxies, drawing them in through gravity, stripping their stars, absorbing their gas and dark matter, and incorporating them into its own structure over billions of years of merger events. The most vivid evidence of this history arrived in 1994, when the Sagittarius dwarf elliptical galaxy was discovered. This small galaxy, currently orbiting the Milky Way at roughly 50,000 light-years from the center, is in the process of being torn apart. Its stars are being stripped out in long streams. The Sagittarius stream, that wrap around the galactic disk several times, tracing the orbit of the dwarf galaxy in trails that span much of the sky when viewed with the right instruments. Some of those stars are now in the solar neighborhood. When astronomers examined the three-dimensional distribution of stars near the Sun with the precision that the Gaia telescope provides, they found a distinctive population with chemical compositions and orbital properties characteristic of the Sagittarius dwarf. Stars that originated in a different galaxy, now incorporated into our own through a merger that is still technically ongoing. There are almost certainly more. Gaia data has revealed the remnants of multiple past merger events encoded in the kinematic and chemical structure of the stellar halo surrounding the galactic disk. Different populations of stars carry the signatures of different progenitor galaxies absorbed at different times across the history of the Milky Way. One particularly clear signal is called the Gaia Enceladus event, a merger with a galaxy of perhaps a quarter the mass of the Milky Way, estimated to have occurred 8 to 11 billion years ago. This merger dramatically reshaped the inner Milky Way and may have triggered a burst of star formation that built much of the thick disk. The older stellar population that sits above and below the thin disk where the Sun currently orbits. The elements that make up the solar system, that make up Earth, that make up the cells of everything alive on this planet, may include material from more than one galaxy. Not all of the Milky Way is originally the Milky Way. Some of it arrived as a guest and was absorbed from a sufficiently precise set of initial conditions. The masses, positions, and velocities of every significant gravitational body. The future trajectory of the Earth can, in principle, be calculated forward in time, not with perfect precision, because gravitational systems of more than two bodies are technically chaotic and accumulate errors in any numerical integration, but with useful accuracy for the near future and with broad accuracy for the very long future. In the short term, the next few 100,000 years, Earth's orbital parameters are fairly well constrained. The eccentricity of its orbit, the inclination, the orientation of its axis, and the precession of the orbital ellipse can all be calculated reliably. These orbital variations, the Milankovitch cycles, have been directly linked to the timing of glacial and interglacial periods over at least the past few million years. The geological record confirms the calculation. The future follows from the same physics. In the medium term, billions of years, the trajectory becomes less precise in detail, but more certain in outline. The Sun will complete roughly 20 more galactic orbits before it expands into a red giant. During those orbits, the solar system will drift through different regions of the galaxy, cross the galactic plane multiple times, be approached by passing stars at irregular intervals, and begin to feel the gravitational effects of the approaching Andromeda galaxy long before any visible merger begins. The very long future. After the red giant phase, after the Sun becomes a white dwarf, after all but the coldest stars have exhausted their fuel, passes beyond any meaningful framework for calculation, but the orbit doesn't end. The white dwarf remnant of the Sun will continue circling in whatever structure the merged Milky Way Andromeda galaxy has become, for timescales that dwarf everything discussed tonight. The path continues. It has no natural terminus built into the physics. Where it ends is a question about the fate of the universe, not about the path itself. The Great Attractor anchors the infall of the local group and Laniakea. But the Great Attractor is not the final word in the gravitational chain. Surveys in the early 21st century, using increasingly deep maps of galaxy distributions and peculiar velocities, revealed that the Great Attractor is embedded in a larger flow, one directed toward an even more massive concentration of matter, roughly 200 million light-years beyond the Great Attractor itself. The Shapley concentration. In its vicinity, the density of galaxies is dramatically elevated compared to the surrounding universe. 10,000 galaxies, some estimates say, compressed into a region that would be considered unusually rich by any standard. The Shapley concentration was identified in the 1,980 seconds and gradually recognized as a likely major contributor to the coherent streaming motion that the Seven Samurai had detected. The question of whether the Great Attractor alone could account for the observed velocities had always been slightly uncomfortable. The numbers suggested that the attractor needed to be even more massive than the Norma cluster region could clearly support. Shapley provided a partial answer. Some of the pull attributed to the Great Attractor may in fact originate from Shapley, acting at greater distance but with such enormous mass that its effect reaches across hundreds of millions of light-years. Whether Shapley is itself falling towards something still larger, whether the chain of gravitational dominoes continues beyond the current edge of precision, is not known. The survey depth needed to resolve this question extends into regions where the measurements become increasingly difficult and where the expansion of the universe competes more aggressively with local gravitational dynamics. We are falling toward the Great Attractor. The Great Attractor falls toward Shapley. What Shapley falls toward, if anything, is not yet known. This is not a comfortable resting place for a chain of causality, but it is an accurate one. There is a moment in freefall, not in falling and hitting, but in the pure freefall before any impact, when the body stops registering motion. The inner ear expects difference. Acceleration, the push of a surface against the body. Free fall gives it nothing of the kind. The result is a sensation of stillness, sometimes of floating, that exists precisely because the fall is total and uniform. You are in something like free fall, not through gravity in the local, human sense, but through the gravitational structure of the galaxy. The supercluster, The cosmic web's accumulated pull, you are carried in a motion so consistent, so encompassing, that every surface you touch, every particle of air, every instrument you might use to measure it is moving at the same speed in the same direction. There is nothing to push against. No differential. The body experiences nothing. The most precise measurements of Earth's galactic velocity are derived not from any sensation or from any instrument on the surface that measures motion in the ordinary sense, but from the cosmic microwave background, from pulsar timing arrays, from very long baseline interferometry of distant quasars, from the orbital mechanics of the solar system measured against reference objects billions of light years away. The motion is real. The instruments confirm it from multiple independent methods. The body provides no information whatsoever. Human perception evolved to detect what mattered in the environment of evolutionary relevance. The approach of predators, the motion of prey, the stability of ground underfoot. None of those pressures required detecting that you are moving through the cosmos at 1,000,000 miles per hour. There was no survival advantage, so the body has no machinery for it. The ground feels solid because it is solid. Relative to your body, the stillness feels real because it is real, relative to everything around you. The difference between this local truth and the cosmic truth is not a contradiction. Both are accurate descriptions of reality in their appropriate frames of reference. The cosmic truth is simply the one that most people go through an entire life without looking at directly. Tonight, in this quiet, you have looked at it directly. The sun will become a red giant in approximately 5 billion years, swelling to engulf the inner planets and possibly Earth itself, depending on how much mass the sun loses as it expands. If Earth survives, it will be a scorched, airless rock in an orbit slightly wider than today. If it is engulfed, its material will become part of the expanding envelope of the dying Sunday. Either way, the red giant phase lasts only 1 to 2 billion years before the outer layers are shed, blown off as a planetary nebula, and the sun's core contracts to a white dwarf. The white dwarf will retain a significant fraction of the sun's original mass, compressed into roughly Earth's current volume, glowing faintly with residual heat. Long after the last planet has been destroyed, long after everything that currently exists in the solar system has ended, the white dwarf remnant of the sun will continue its galactic orbit. It will bob through the galactic plane. It will be pulled, faintly, by the motion of whatever Laniakea has become by then. It will orbit in whatever structure the merged Milky Way Andromeda galaxy has taken on across the following billions of years. The orbit doesn't know that the solar system is over. Gravity doesn't require observers. The helical path that Earth has been tracing, the corkscrew we began with, continues in the remnant after everything that currently exists in the solar system has ended. The trajectory has a momentum that no planetary death can interrupt. This is not a comforting thought or an uncomforting one. It is a fact about physics. The path is older than the objects that currently trace it, and younger than the objects that will eventually trace it after all of this is gone. None of those objects have any say in whether the path continues. The solar system formed in a molecular cloud approximately 4.5 billion years ago. The material that became the sun and the planets had its own velocity within that cloud, and when the cloud collapsed under gravity, that velocity was incorporated into the angular momentum of the forming system. The sun's current galactic orbit, the direction it faces, the plane it travels in, these were set, in rough terms, at the moment of formation by the conditions of that original molecular cloud. The original molecular cloud does not exist anymore. It was consumed in the process of forming the solar system and, presumably, other stars. The position in the galaxy where the solar system formed is long gone from the solar system's current location. It has moved on, in its own orbit, for 4.5 billion years. There is no location to return to. There is no original address. This is true of every moving thing in the universe. Motion does not preserve the memory of origin. The current state of any system is a snapshot of its trajectory, not a record of where the trajectory began. You can calculate backward, in principle, and reconstruct the approximate origin. Astronomers do this for comets, tracing their paths back to the Oort cloud. For stars, tracing their paths back to birth clusters. But the calculation has to be performed externally. The object itself carries nothing that marks its birthplace. Earth has been moving for 4.5 billion years without a single physical indication of where it started. There is no pointing back. There is no finding the origin by feel or instinct, or any property inherent to the planet itself. The path is only forward, and the memory of origin lives only in the current conditions, waiting to be decoded by instruments patient enough to read it. Every atom in your body is moving, not just through space with you, as part of the solar system's galactic journey, but internally, vibrating and rotating in ways that thermal energy drives continuously at room temperature. The carbon in your cells, the oxygen in your blood, the calcium in your bones. These atoms are in constant motion at the molecular scale, motion that biology depends on but never registers as sensation. These atoms are also old travelers. The carbon was synthesized in the cores of stars that died before the sun was born. Red giants and asymptotic giant branch stars that processed hydrogen into helium into carbon over hundreds of millions of years, and then shed that material into the interstellar medium through stellar winds and planetary nebulae. The oxygen came from more massive stars, whose cores fused heavier elements and whose explosions as supernovae released them into the surrounding gas. The iron in your blood came from the thermonuclear detonations of white dwarfs in binary systems, a specific and violent alchemy that occurred in stars that themselves lived and died billions of years before the Earth formed. These elements drifted in the interstellar medium, were incorporated into molecular clouds, collapsed into the solar system's forming disk, and eventually found their way into the chemistry of Earth's early oceans, and then into the biology of every organism this planet has ever produced. The journey of the atoms that make you is longer than the journey of the Earth. Before there was a solar system to orbit in, these atoms were already moving, through the interstellar medium, inside the cores of dying stars, in the molecular clouds that preceded the sun's formation. The motion that currently carries you through the Laniakea supercluster at 1.3 million miles per hour is a recent chapter in a much older itinerary. You are not just traveling through the cosmos, you are made of the cosmos that is doing the traveling. Assembled from material that has been in motion since the first stellar winds carried processed elements out into the interstellar medium, billions of years before this planet existed to give you a place to rest. The motion of the solar system through the galaxy is directly visible in the night sky, if you know how to read it. Stars are not fixed. Each has its own velocity, a proper motion across the sky, reflecting the combined effects of the star's own galactic orbit and the solar system's motion. Most proper motions are too small to see without instruments over human timescales. But over centuries and millennia, stars drift. The constellation shapes visible to ancient astronomers are slightly different from the shapes they will take in 50,000 years. The Big Dipper will be unrecognizable in 100,000 years. Every sky that has ever been observed was already different from the one before it. This drift is the visual record of motion, yours and theirs, superimposed. When an astronomer measures the proper motion of a nearby star, the angle per year by which it shifts against the background, they are measuring the relative velocity between the solar system and that star. The solar apex, the direction of the sun's motion through its local stellar neighborhood, is toward the constellation Hercules. This direction produces a characteristic pattern in stellar proper motions. Stars ahead appear to diverge, stars behind appear to converge, a perspective effect identical to the way a road appears to open in front and close behind a moving vehicle. The night sky is the instrument. It records where we are going. The specific direction of travel, combining the galactic orbit, the great attractor infall, and the broader Laniakea flow, is toward a region of sky in the general direction of Virgo and beyond, extending toward Shapley in the far background. The pattern of galaxy velocities around us, the CMB dipole, and the broader peculiar velocity field all agree on this direction. We move. The sky shows it, for anyone patient enough to measure it. None of this changes over a human lifetime in any way the eye can detect, but it is happening every night, in every star's almost imperceptible drift. The path is written in the sky. We are simply moving too slowly, in the relevant frame, to watch ourselves move. At the very front of the heliosphere, the compressed side facing the direction of the solar system's travel through the interstellar medium, there is a feature called the termination shock, and just beyond the heliopause, perhaps a bow shock. This is where the solar system announces its presence to the galaxy. As the solar system moves through the interstellar medium at roughly 12 miles per second relative to the local standard of rest, the average velocity of nearby stars, the heliosphere plows through whatever gas and dust lies in its path. The interaction between the oncoming interstellar medium and the outflowing solar wind creates a structure at the leading edge, a region of compression, heating, and turbulence, where the two plasmas first meet. Whether a true bow shock forms depends on whether the solar system's speed through the interstellar medium is supersonic with respect to the local interstellar medium's own sound speed. In the current environment, the warm, partially ionized gas of the local interstellar cloud, the relative velocity appears to be slightly below the threshold for a strong bow shock, though this is still debated. Some models predict a weak bow shock or an astrosphere, rather than the sharp shock structure the term implies. The Voyager probes, having now spent years in the interstellar medium, are returning data that is gradually refining this picture. What is not in doubt is the asymmetry. The leading edge of the heliosphere, compressed by the ram pressure of the oncoming interstellar medium, is significantly blunter and closer to the Sun than the trailing edge. The heliopause is estimated to be about 11 billion miles from the Sun on the leading side, and stretches into a long tail of uncertain extent on the trailing side. Some models put it at hundreds of billions of miles. Others suggest it may extend to thousands of AU before dissipating completely into the interstellar medium. This asymmetry is the signature of motion. A stationary sun in a stationary medium would produce a symmetric heliosphere, a bubble expanding equally in all directions. The asymmetry we observe is the imprint of the journey on the structure we live inside. The heliosphere is shaped by the fact that we are moving in a specific direction, and has been shaped by that motion for as long as the Sun has been emitting a solar wind. The leading edge, the compressed, turbulent, energetically active front, is the first part of the solar system to encounter whatever lies ahead on the orbital path. In a very direct sense, it is the prow of everything humanity has ever built or known, moving through the interstellar medium at 12 miles per second, encountering what comes next before any planet, any comet, any rock in the Oort cloud knows it is there. The Sun's motion is not just galactic, it also has a local component, a velocity relative to the nearest stars in the solar neighborhood. This local motion is called the solar apex, the point in the sky toward which the Sun is moving relative to nearby stars. And its opposite, the solar antapex, is the direction from which the Sun is coming. The solar apex is located in the constellation Hercules, more precisely, near the star Vega in the constellation Lyra, though the exact coordinates depend on which reference frame is used. The velocity is approximately 12 to 20 kilometers per second, depending on whether the calculation is made relative to the local standard of rest, the average motion of stars in the solar neighborhood, or relative to specific nearby stars. This local motion is layered on top of the galactic orbital velocity, which is roughly 5 times larger. From outside the galaxy, the dominant motion of the solar system is the galactic orbit. But within the solar neighborhood, among the roughly 50 to 100 stars closest to the Sunday, the local apex velocity is what produces the patterns in stellar proper motions that ancient astronomers first noticed, and that Friedrich Bessel began to quantify in the 19th century. The existence of a solar apex was first established by William Herschel in 1783, who analyzed the proper motions of a handful of stars and noticed that they showed a systematic pattern consistent with the Sun moving toward a point in Hercules. This was the first measurement of the Sun's local velocity through space, a remarkable achievement given that the tools available to Herschel were a telescope and careful records, with no understanding of what the motions implied about the galaxy's structure. The solar apex also defines the direction of something important for the heliosphere, the direction from which the interstellar medium appears to flow past us. As the Sun moves toward Hercules, the interstellar medium flows past from that direction, which means the bow shock, the compression of the heliosphere's leading edge, faces generally toward Hercules. The direction of Earth's journey through its local neighborhood is written in the shape of the bubble we carry. The Milky Way does not rotate like a rigid disk, not the way a spinning plate rotates, with every part completing one turn in the same time. Instead, the galaxy exhibits what astronomers call differential rotation. Different parts of the disk orbit the galactic center at different speeds, meaning stars at different radii complete their orbits on different timescales. This is what Vera Rubin's rotation curves measured in detail, the relationship between a star's distance from the galactic center and its orbital velocity. In a galaxy with differential rotation and a flat or rising rotation curve, stars at the inner disk orbit faster than stars at the outer disk, meaning that over time, the inner disk laps the outer disk, creating shearing motions throughout the disk. For the spiral arms, this has an important consequence. If the spiral arms were fixed patterns of stars, if the same stars always composed the same arm, differential rotation would wind them up tightly over just a few galactic rotations, destroying the open spiral pattern within a few billion years. The fact that the Milky Way has maintained open spiral structure for billions of years is evidence that the arms are not composed of fixed stars. They are density waves, as described elsewhere, patterns that move through the disk at a different speed than the stars themselves. For the Sun specifically, differential rotation means that its position relative to the spiral arms is not fixed. The Sun's orbital velocity and the pattern speed of the spiral arms are different, meaning the Sun slowly drifts in and out of arm regions on timescales of hundreds of millions of years. The Sun is currently in or near the inner edge of the Orion arm, but a billion years ago it was in a different arm environment, and a billion years hence it will be in another. Differential rotation also means that the stars that were once near the Sun in the galaxy, the birth cluster from which the Sun originally emerged, have been scattered across the disk. The gravitational perturbations of spiral arm crossings, molecular cloud encounters, and the overall shearing of the disk have dispersed that original cluster over billions of years. The Sun's birth siblings, the stars that formed from the same molecular cloud, are now distributed across a wide swath of the galactic disk, and identifying them requires precise chemical analysis, which several teams are attempting using Gaia data. We were born in a neighborhood. That neighborhood is now a dispersed population spread across a large fraction of the galaxy's disk, separated not by choice but by the relentless shearing of differential rotation over 4.5 billion years. The concept of a habitable zone is usually applied at the scale of a planetary system. The range of distances from a star at which liquid water could exist on a planetary surface, but astronomers have proposed an analogous concept at the galactic scale, a galactic habitable zone, a range of distances from the galactic center within which the conditions for complex life are most likely to be met. The argument is based on several factors that vary with galactic radius. Too close to the galactic center, and the environment is hostile. The density of stars is extreme, supernova rates are high, gravitational dynamics are turbulent, and radiation levels from the dense stellar population and the active galactic center make the long-term stability of planetary systems much less likely. The galactic center is active in ways that would likely preclude the multi-billion-year continuity that complex life requires. Too far from the galactic center, and a different problem emerges. The interstellar medium is too thin. the metallicity too low. Stars in the outer disk formed from material that has been less processed by earlier generations of stellar evolution, meaning they tend to be metal poor, with less of the heavy elements needed to build rocky planets and the chemistry of life. The outer disk is also less dynamically connected to the rest of the galaxy in ways that may affect the availability of certain types of matter. The Sun currently sits at roughly 26,000 light-years from the galactic center, in a region some researchers identify as within the galactic habitable zone, far enough from the center to avoid the worst of the radiation and gravitational turbulence, close enough to have formed from material with sufficient heavy element abundance to produce a rocky planet with iron, calcium, carbon, and the other elements that biology requires. The concept of a galactic habitable zone remains an active area of research, and its boundaries are not defined with precision, but the framework is coherent. The Sun's position in the galaxy, maintained for billions of years in the relatively quiet outer half of the disk, may be part of what has allowed this particular rocky planet to maintain the conditions for life long enough for something like this to emerge from it. At the approximate center of the Laniakea Basin of Attraction sits the Virgo cluster, one of the nearest large galaxy clusters to the Milky Way, at roughly 53 million light-years from Earth, containing at least 1,300 galaxies, and anchoring the broader Virgo supercluster, of which the local group is an outlying member. The Virgo cluster is the most massive object within 100 million light-years of the Milky Way. Its total mass, including the dark matter halo that extends far beyond the visible galaxies, is estimated at roughly 10,000 trillion times the mass of the Sunday, several times more massive than the entire local group. The gravitational pull of the Virgo cluster is measurable. The Milky Way is moving toward it at approximately 220 kilometers per second, relative to the cosmic expansion, a peculiar velocity that represents one layer of the broader infall into the Laniakea structure. The Virgo cluster is not the same as the Great Attractor. The Great Attractor lies further away, roughly 250 million light-years, anchoring a different and larger part of the Laniakea flow. The Virgo cluster anchors the local flow, the motion of the Milky Way and its immediate cosmic neighborhood toward the nearest major gravitational concentration. The Virgo cluster itself is also in motion, not stationary in the Laniakea frame, but participating in the broader infall toward the Great Attractor. Everything in the local universe is falling towards something more massive, and that something is falling towards something more massive still. The structure of the infall is hierarchical. The local group falls toward Virgo. Virgo participates in the Laniakea flow. Laniakea flows toward the Great Attractor, and the Great Attractor region flows toward Shapley. At the center of the Virgo cluster sits a massive elliptical galaxy called M87, home of the first black hole ever directly imaged, photographed by the Event Horizon Telescope in 2019. That black hole, visible as a glowing ring of superheated gas, has a mass of 6.5 billion solar masses, more than 1,500 times the mass of Sagittarius A at the center of the Milky Way. It is the anchor of the anchor, the most massive object at the gravitational heart of the nearest large basin. The light from M87 that reaches Earth tonight left that galaxy 53 million years ago. The journey has been carrying us toward it, slowly and continuously. For the entire time, we will never arrive. The expansion will prevent it, but the motion toward the Virgo cluster is real, ongoing, and measurable from this planet every time a telescope is turned toward the Virgo constellation. The Milky Way is our home galaxy, and we cannot weigh it precisely. Estimates of the Milky Way's total mass, including all stars, gas, dust, and dark matter, range from roughly 500 billion to 2 trillion times the mass of the Sun, depending on the method used and the assumptions made about the extent of the dark matter halo. A factor of 2, in astronomical terms, is not an unusual uncertainty. It reflects the genuine difficulty of measuring a structure from the inside, using tracers that become increasingly sparse at large distances. The core problem is the dark matter halo. The visible galaxy, all the stars, gas, and dust that can be directly observed contributes only perhaps 10% of the total mass. The remaining 90% is in the dark matter halo, which extends far beyond the visible disk and whose outer edge is not clearly defined. To measure the halo's total mass, astronomers need tracers at large distances from the galactic center, satellite galaxies, globular clusters, and hypervelocity stars. Stars moving so fast they have been ejected from the galactic center on escape trajectories whose speeds constrain the escape velocity and thus the total enclosed mass. Different methods give different answers. Some studies, using globular cluster kinematics, find a relatively low mass toward the lower end of the range. Others, using satellite galaxy orbits, find significantly higher values. The Gaia telescope has improved the precision of many individual measurements, but the discrepancy between methods has not fully closed. Part of the issue may be that the Milky Way is genuinely less massive than some estimates assumed, which would have implications for our understanding of its merger history and its future interaction with Andromeda. This is a useful fact to hold alongside everything else in this episode. We know the shape of the path, the scale of the galactic year, the direction of the great attractor's pull, but the total mass of the galaxy we orbit in, the fundamental quantity that determines the shape and duration of that orbit, remains uncertain within a factor of 2. Astronomy is a science that works at the limits of what instruments can reach. At those limits, uncertainty is not failure. It is an accurate description of how far we have gotten. The journey of the solar system through the galaxy leaves traces, not in the rocks of Earth alone, but in the ice. When cosmic rays, high-energy particles from outside the heliosphere penetrate the atmosphere, they initiate cascades of secondary particles that produce certain radioactive isotopes in the upper atmosphere, most notably beryllium-10 and chlorine-36. These isotopes are deposited on Earth's surface through precipitation, and in regions like Antarctica and Greenland, they accumulate in ice layers that record their deposition rate over hundreds of thousands to millions of years. The flux of cosmic rays reaching Earth's atmosphere is modulated by several factors. The strength of the heliosphere, the strength of Earth's magnetic field, and the flux of galactic cosmic rays entering the heliosphere from outside. When the heliosphere is stronger, during periods of higher solar activity, or when the external medium is thinner, fewer cosmic rays penetrate to the surface and isotope production rates are lower. When the heliosphere is compressed by a denser external medium, or when solar activity is weaker, cosmic ray flux and isotope production rates increase. Records of beryllium 10 inches ice cores going back 800,000 years show clear correlations with the solar cycle and with Earth's magnetic field reversals. At longer timescales, tens of millions of years, the record becomes harder to read because the ice itself doesn't survive that long. But isotopes preserved in deep-sea sediments and in the lunar regolith offer windows into cosmic ray flux over much longer periods. Some researchers have searched for signals in these long-duration records that might reflect the solar system's galactic environment. Specifically, whether the cosmic ray flux systematically varies with the proposed crossing times of the galactic plane or spiral arm regions. The results are suggestive, but not conclusive. Isolating a galactic signal from the geological noise is technically difficult, and the timescales involved push the resolution of existing records. But the principle is sound. The galaxy writes itself into the ice. The path we have traveled leaves chemical signatures in the sediment and in the frozen layers of a continent. The history of where the solar system has been is not entirely lost. It is waiting, in isotope ratios, for instruments precise enough to decode it fully. On a dark, clear night, before or after twilight, a faint, diffuse cone of light is sometimes visible along the plane of the ecliptic, extending upward from the horizon in the direction of the sun's recent setting or coming rising. This is the zodiacal light, and it is caused by sunlight scattered by a diffuse cloud of fine dust particles spread throughout the inner solar system, concentrated near the ecliptic plane. The zodiacal dust cloud is continuously replenished, comets sublimating as they approach the sun release gas and dust, and the solid debris trails left along their orbits gradually spread out over time to fill the ecliptic plane. Asteroid collisions in the asteroid belt produce additional fine particles. The solar wind and radiation pressure gradually sweep smaller particles out of the inner solar system, while larger particles spiral inward through the Poynting-Robertson effect, a gentle but persistent deceleration caused by the anisotropic absorption and re-emission of sunlight. This dust cloud moves with the solar system through the galaxy. It is a component of the material the heliosphere carries, not as compact as the planets, not as extended as the Oort cloud, but present throughout the inner solar system in a disc-shaped distribution that follows the orbital plane. Interestingly, the zodiacal dust cloud also receives contributions from interstellar sources. Interstellar dust grains, particles from the local interstellar medium, can penetrate the heliosphere and have been detected directly by the Ulysses and Galileo spacecraft. These interstellar particles stream into the solar system from a specific direction, consistent with the direction of the heliosphere's motion through the local medium. They are small enough to pass through the magnetic fields that deflect charged particles, and they carry chemical signatures distinct from the cometary and asteroidal material that dominates the zodiacal cloud. The zodiacal dust is thus a mixture. Material native to the solar system, mixed with interstellar grains that have wandered in from the surrounding medium. The inner solar system is not isolated from the galaxy. The dust that scatters the zodiacal light contains particles that originated in other stellar systems, carried here by the same relative motion that compresses the heliosphere's leading edge. You can see the galactic environment entering the solar system. On a clear, dark night, facing the right direction at the right time, the zodiacal light is the visible trace of the interstellar medium flowing through the outer heliosphere and depositing itself, grain by grain, into the cloud of dust that orbits the Sunday. The center of the Milky Way is not simply a point of concentrated mass. It contains an elongated structure called the galactic bar, a roughly rectangular distribution of stars and gas, extending from the galactic center outward to roughly 10,000 light-years in two directions, oriented at an angle to the Sun's line of sight. The galactic bar rotates, not at the same rate as the surrounding disk. It has its own pattern speed, completing one rotation in a different period than the stars that compose it. This differential rotation between the bar and the surrounding disk creates a complex set of gravitational resonances throughout the inner galaxy, regions where the orbital period of stars is a simple fraction of the bar's rotational period. 1:1, 2:1, 4:1, and where the bar's periodic gravitational tugs accumulate over time rather than averaging out. These resonances affect orbital dynamics across a significant fraction of the disk. Stars in resonance with the bar can have their orbits subtly but persistently altered. Their eccentricities increased, their radial positions slowly shifted. The Sun's position at 26,000 light-years from the galactic center places it near or somewhat outside the outer Lindblad resonance of the bar, a region where the bar's influence is weaker but not negligible over galactic timescales. This matters for the Sun's galactic orbit in a specific way. The orbit is not a clean, undisturbed ellipse, even without considering the vertical oscillations and radial breathing mentioned elsewhere. The bar's gravitational influence introduces additional perturbations, small, slow, but accumulating over the galactic year. Over multiple orbits, these perturbations contribute to the chaotic sensitivity of the galactic orbit. The reason that predicting the Sun's precise position billions of years in the future requires increasingly uncertain numerical integration. The bar's existence was suspected for decades based on the distribution of stars in the galactic bulge, confirmed through infrared surveys that could penetrate the dust obscuring the central regions. Its exact length, orientation, and pattern speed are still refined with each new dataset, particularly from the Gaia telescope, which is mapping the three-dimensional distribution and motion of stars across a significant fraction of the Milky Way's disk. The galactic bar is part of the mechanism. The spiral arms are part of the mechanism. The dark matter halo is part of the mechanism. The Sun's orbit runs through all of these simultaneously, perturbed by each, shaped by none completely. The path is the sum of all of it. Too complex to draw, too real to ignore, too large to fully measure from the inside. The heliosphere's current structure, its size, shape, and protective capacity, is not fixed. It responds to the solar cycle on timescales of 11 years, expanding and contracting as solar activity rises and falls, but on much longer timescales, it responds to the changing external medium as the solar system moves through different regions of the galaxy. In the current epoch, the solar system sits in the local interstellar cloud, a warm, partially ionized region of gas. This cloud supports a heliosphere of roughly the size the Voyager probes have measured, about 11 billion miles to the heliopause on the compressed leading side. When the solar system exits the local interstellar cloud, which models suggest could happen within the next few thousand to tens of thousands of years, the external medium may change significantly. If the solar system exits into the hot, thin plasma of the surrounding local bubble, the lower density external medium would allow the heliosphere to expand dramatically. A larger heliosphere provides stronger shielding against cosmic rays, potentially reducing the flux reaching the inner solar system and Earth's surface. Conversely, if the solar system were to enter a denser molecular cloud, as it has almost certainly done at various points over billions of years of galactic travel, the heliosphere would be compressed, possibly to within the orbits of the outer planets in an extreme case. In such scenarios, cosmic ray flux at Earth's surface would increase substantially, possibly affecting the atmosphere's chemistry and the surface radiation environment. These transitions are not abrupt. The interstellar medium changes gradually, as the solar system's path carries it through different environments and the heliosphere adjusts on timescales that are slow compared to a human life, but rapid compared to a galactic orbit. The protection the heliosphere provides, the invisible shield that has surrounded Earth for the entire history of life on this planet, has always been variable. It will always be variable. The path ahead passes through environments we cannot fully predict, because we cannot fully map the interstellar medium along the solar system's future trajectory. The shield breathes. The path continues. The corkscrew is not new. It is not a recent discovery that revealed something previously otherwise. The path has been this shape since the solar system formed, since the original molecular cloud collapsed, and the angular momentum of the forming disk resolved into the orbital geometry that has persisted for 4.5 billion years. What changed was not the path. What changed was our ability to measure it. Before the early 20th century, the scale of the galaxy itself was not known with any precision. Before Vera Rubin's work, the dark matter halo that determines the shape of the galactic orbit was not understood. Before the Seven Samurai, the Great Attractor was not identified. Before the Gaia telescope, the three-dimensional orbital histories of billions of stars were not accessible. Before the Fermi satellite, the enormous structures that the galactic center has already released into the halo were invisible. Each of these discoveries did not change the path. They revealed what had always been true. The corkscrew was always a corkscrew. The Milky Way was always falling toward the Great Attractor. The dark matter halo was always there, holding the galaxy together. The atoms in your body were always made in dying stars. The heliosphere was always ploughing through the interstellar medium. The Oort cloud was always carrying its primordial ice through the galaxy at the edge of the solar system's reach. All of this was happening before any of it was known. It will be happening long after the instruments that measure it are gone. The shape of the path is not news. It is simply what has always been. We began with a correction. We began with the shape of the path. The fact that the diagram you were given in school, the closed ellipse, the clean circle, was wrong in a way that matters, not slightly wrong. Geometrically, physically, permanently wrong. And now, Having followed the path through the helix and the galactic year, through the bobbing midplane and the density waves, through the local group, falling toward its neighbors, and the Milky Way embedded in Laniakea, and Laniakea itself flowing toward Shapley. Having sat with the number 1.3 million miles per hour and felt what it actually means when every layer of motion is stacked together, the ground beneath you is still the same ground. The shape of the path has always been this. The corkscrew was tracing itself before the first cell divided, before the first ocean formed, before the planet cooled enough to hold liquid water. It was tracing itself before there was anything on this surface to notice it. And it will trace itself after every surface on Earth has been changed beyond recognition. The atoms that make you have been in motion longer than the solar system. The path that carries you tonight has no beginning you can return to, and no end that is approaching on any scale a life can hold. It continues in the dark, quietly, at speeds the body was not built to feel, through a structure so large that naming it, Laniakea, the cosmic web, the observable universe, does almost nothing to make it smaller. This particular corkscrew, this exact location in the galaxy at this exact moment in the galactic year, has never been before. It will not be again. The galactic bar perturbs it gently, without announcement. The dark matter halo holds it, invisibly, on a scale no instrument has fully mapped, and somewhere ahead, in a direction the CMB has already named, the path continues into territory the solar system has not yet entered. If your eyes are growing heavy, let them close. The motion will continue without your watching it. The heliosphere will push against the interstellar medium. The Sun will complete another small arc of its galactic year. The Milky Way will drift another imperceptible fraction of a degree toward the Great Attractor. None of it requires you to be awake. The path carries everything. It always has. If this felt like the kind of night you come back to, leave a comment when you wake up. If you're still here, the next chapter is waiting. The universe will still be here when you wake up. So will we. Good night.